This is an inclined plane. This machine is an inclined plane. How do we determine the velocity ratio in an inclined plane? A lot of students find this difficult. They find it difficult because they don't understand what the effort distance is and how to identify the components of this inclined plane that represents the effort distance and the components of this inclined plane that represents the distance the load actually travels. But in this video, I'm going to make it very simple for us to understand. The first thing you need to know is to understand what velocity ratio is. This V area is velocity ratio. Velocity ratio is defined as the ratio of the distance traveled by the effort to the distance traveled by the load. The load is the object you're moving. The effort is the force you applied, the applied force. So that is what we have this formula here. We have this formula here for velocity ratio. Now, what do we do next? Let's look at this situation, this inclined plane, and see. This is the load here. The load is supposed to be here. The load was here initially. So let's see how to determine the effort distance, the distance traveled by the applied force. Let's say I apply a force like this to move this object. If this load here moves from here to here, you agree with me that the effort has traveled from here to here. This will be the position of the effort. If you also move this load to this point here, the effort that was applied here has moved from here to here. So this will be the final position of the effort. So what I'm trying to say, what I'm trying to say is that the distance along the plane, which is the hypotenuse side, represents the effort distance. So we conclude that from here to here is the effort distance. We say it is ED, effort distance. But now let's determine how to get the load distance. The load was here. This was the position of the load. But the load has moved from here to this height. Now, don't forget that the essence of using an inclined plane is to take an object, a load, like a bag of rice and other things, to a particular height, like the height of a lorry, to move it to a height. So the load is actually traveling a vertical distance, a vertical distance. So if the load was here, let's trace it like this. So the load was here. At the end of everything, the load gets here. So the load has actually traveled a vertical distance, which is equal to h, which is equal to h according to this diagram. So the distance moved by the load is what we call the load distance. So I will call this the load distance LD. If I come to my formula, let's look at this, understand this. If I come to my formula, this velocity ratio, which is effort distance over load distance, my effort distance is ED, which is equal to X, while my load distance is equal to the vertical height. My velocity ratio now is equal to X over H. Okay, so let's look at this inclined plane. This is theta here. The plane makes an angle of theta with the horizontal. So if I look at this inclined plane, this is the opposite side of the right angle triangle, while this is the hypotenuse side. So if I apply my trigonometric ratio, but now, remember that this formula means that velocity ratio is x over h. This sine theta has an invisible one here. So what I'm going to do is to invert this part, to turn this part upside down and also turn this part upside down. If you look at this x over h now represents our velocity ratio. What do we conclude? We conclude therefore that the velocity ratio in an inclined plane is 1 over sine theta. 1 over sine theta, where theta is the angle made with the horizontal.